Hey fellow nerds, let us continue our discussion on Opamp applications. Today we will cover Schmitt Trigger. But before that, let us take our comparator circuit again. Here input is given to the non-inverting terminal, so we have a non-inverting comparator. We learned that if input is greater than the reference voltage, differential input will be positive and therefore output will be positive saturation voltage. When input is less than the reference voltage, differential input will be negative and output will be negative saturation voltage. If we have an ideal sinusoidal input signal like this, and this is the reference voltage, then output will look like this. Every time input crosses the reference voltage, output will change its state. Now, real signals are never this perfect. They can be slow, they can be noisy, or both. For example, let us assume that this input is noisy. Let's take a closer look. The ideal signal only crosses the reference voltage one time over here. But the noisy signal crosses 1, 2, 3, 4, 5 times. Over here, ideal signal crosses the reference voltage one time, but the noisy signal does 1, 2, 3 times. Again over here, the noisy signal crosses the reference voltage 1, 2, 3 times. The output of the comparator will look like this. When input signal is clean and crosses the reference voltage quickly, comparator gives a neat, sharp output change. But when the input signal is slow or noisy, it stays near the threshold for too long and the comparator keeps switching on and off. That's what is happening at all these points. This phenomenon is called chatter. We saw this happening for a noisy input. It can also happen for a slow input. It may hang around the threshold for longer, and this can also cause chatter. So a simple comparator cannot handle noisy or slowly changing signals. It panics near the threshold. We need a technique to avoid this. This is the idea. Assume that instead of 1, we have 2 reference voltages. Now imagine the output will change only when input becomes greater than the first reference voltage for the first time, and when input becomes less than the second reference voltage for the first time. Let me explain. Take a look at the signal. It becomes greater than the first reference voltage, which is the higher reference voltage, for the first time at this point. That means that is the point at which the output changes for the first time. Assuming initially the output is negative saturation voltage, it will change to positive saturation voltage. The signal crosses first reference voltage again at all these points. But it doesn't matter because output changes only when this happens for the first time. The next time it changes is when input becomes less than the second reference voltage for the first time. And that happens over here. Output changes from plus Vsat to minus Vsat. Input again crosses the second reference voltage at these points, but it doesn't matter. The next time output changes is when input becomes greater than the first reference voltage again for the first time. And that happens over here. Output changes from negative Vsat to positive Vsat. This way, we can avoid chatter. This is only the idea. We have to design a circuit that does it. A circuit that does this is called a regenerative comparator or a Schmitt trigger. To build a Schmitt trigger, we'll start with an Opamp. We'll give the input to the inverting terminal. Unlike a normal comparator, here we will give a feedback. But there is a twist. Till now, we have only seen negative feedback, the kind that stabilizes the Opamp, reduces the gain, and makes circuits like buffers and amplifiers. Negative feedback tries to cancel the changes in the output. When output rises, it brings it down. Schmitt trigger is basically a comparator. We want the output to be always saturated. Instead of a negative feedback, we will use a positive feedback. What is the difference? A positive feedback tries to reinforce the changes. We can say that when negative feedback fights changes, positive feedback amplifies them. When the output becomes positive, the positive feedback encourages it to become even more positive until it finally reaches plus Vsat and can't go any higher. The same way, when output becomes negative, the positive feedback pushes it even more negative until it reaches minus Vsat and can't go any lower. That means with positive feedback, the output is always forced to become one extreme or the other. The output will always be either positive saturation voltage or negative saturation voltage. To give a positive feedback, let us first take output through a voltage divider, R1 and R2. Vout will be divided between R1 and R2. Out of that, whatever is dropped across R2 will be fed back to the non-inverting terminal. This gives the circuit a positive feedback. Let us call this point X. So the potential here will be Vx. At the inverting terminal, we have input. At the non-inverting terminal, we have Vx. So Vx will be the reference voltage here. Since this is a voltage divider, Vx will be Vout divided by R1 plus R2 multiplied by R2. Again, feedback is positive, which means the output is always saturated. It will be either plus Vsat or minus Vsat. Now, when output is plus Vsat, what will be Vx? It will be plus Vsat divided by R1 plus R2 multiplied by R2. When output is negative Vsat, Vx will be negative Vsat divided by R1 plus R2 multiplied by R2. These are the only options we can have for Vx, which is the reference voltage. Basically, by applying the feedback, we got two reference voltages. They are equal in magnitude and opposite in sign. Now, basically, this is a comparator. Specifically speaking, this is an inverting comparator because input is in the inverting terminal. That means when input is less than the reference voltage, output will switch to plus Vsat. When input is greater than the reference voltage, output will be negative Vsat. This is a very simple but one of the most important points that you have to remember to save yourself from many confusions later. When output is plus Vsat, the next time output switches is when input becomes greater than the reference voltage. When output is negative Vsat, the next time output switches is when input becomes less than the reference voltage. Let us now bring in the noisy input signal and try to plot the output. Assume that initially output of the comparator is plus Vsat. Then Vx will be plus Vsat divided by R1 plus R2 multiplied by R2. Let's call it reference voltage 1. Let me call it Vx1 and mark it on the graph like this. Output is plus Vsat now. That means the next time output switches is when input becomes greater than the reference voltage, which is Vx1. When input crosses the reference voltage, output will switch from plus Vsat to negative Vsat, and that happens at this point. Let us show the output till then. Just like we assumed, when input became greater than the reference voltage, output switched. That means now the output is negative Vsat. But when output is negative Vsat, Vx will be negative Vsat divided by R1 plus R2 multiplied by R2, which means it is not just the output that switched, reference voltage also changed. Let us call this reference voltage 2. I'll call it Vx2 and mark it on the graph like this. This is our new reference voltage. You can see the input crosses Vx1 again at all these points. But output will not change. Why? Because Vx1 is no more the reference voltage. Reference voltage is Vx2 now. Output is minus Vsat right now. So the next time it switches is when input becomes lesser than the reference voltage, which is Vx2. And that happens at this point. And that is when the output switches again. Till then, output will be negative Vsat. So when input became lesser than negative Vsat by R1 plus R2 multiplied by R2, which is Vx2, output switches again. That means now the output is positive saturation voltage. And that means Vx becomes positive saturation voltage divided by R1 plus R2 multiplied by R2, which is our first reference voltage. When output switches, reference voltage also switches. Again, Vx1 becomes our reference voltage. Input crosses Vx2 again at all these points. But output will not change because Vx2 is no more the reference voltage. The next time output changes is when input becomes greater than Vx1, which happens over here. Till then, output will be plus saturation voltage. and at that point it will switch again. So every time output switches, reference voltage also switches. And you can see, even though input signal is noisy, there is no chatter in the output. This is how a Schmitt trigger works. We can call Vx1 the upper threshold voltage and Vx2 the lower threshold voltage. This circuit works the way we imagined. Output changes only when input becomes greater than the upper threshold voltage for the first time and when input becomes less than the lower threshold voltage for the first time. And it works so because the reference voltage keeps switching between the positive and negative values every time there is a trigger. Now, this circuit has one limitation. Upper threshold voltage and lower threshold voltage are always equal and opposite. What if I want more control over the threshold voltage? What if I don't want them equal and opposite? Let us see how that can be done. This is the only change we have to make. Instead of grounding this point, we'll apply a reference voltage there that is under our control. Let's call the current flowing through R1 I1 and the current flowing through R2 I2. We already know no current can flow into the input terminal because an ideal op-amp has infinite input impedance. That means I1 is equal to I2. I1 is the current through R1. R1 has a potential V out here and Vx here. So I1 is V out minus Vx divided by R1. I2 is the current through R2. R2 has Vx potential here and V reference here. So I2 is Vx minus V reference divided by R2. But these two are equal. Let's take R2 to this side and R1 to the other side. We get V out R2 minus Vx R2 is equal to Vx R1 minus V reference R1. From here, let's write an expression for Vx. Vx will come out to be V out divided by R1 plus R2 multiplied by R2 plus V reference divided by R1 plus R2 multiplied by R1. Vx is the actual reference voltage we give at the positive terminal. Earlier, it was just V out by R1 plus R2 multiplied by R2. But this time, we have an extra term that depends on the reference voltage we give. Now, V out can take two values, plus Vsat or minus Vsat. Depending on that, we can get upper threshold voltage and lower threshold voltage. When V out is plus Vsat, we get the upper threshold voltage. When V out is negative Vsat, we get the lower threshold voltage. These two will not be equal and opposite. For example, assume that magnitude of this is 5 and magnitude of this is 3. The upper threshold voltage will be 5 plus 3, which is 8, and the lower threshold voltage will be minus 5 plus 3, which is minus 2. Threshold voltages will not be symmetric anymore. We can design the circuit such that we get to control the threshold voltages individually. When the V reference we apply is 0, we get equal and opposite threshold voltages. When we apply a non-zero reference voltage, we get more control over the threshold voltages. Let us take a random signal and compare the output of a normal comparator and a Schmitt trigger if this is given as an input to both of them. If the applied V reference is 0, for a normal comparator, reference voltage will be 0 volt. Every time the input signal crosses 0 volt, output will switch. Comparator output will look like this. For a Schmitt trigger, if applied V reference is 0, we will still have two threshold voltages. The only thing is they will be equal and opposite. The output will switch every time input becomes greater than the upper threshold voltage for the first time and when it becomes lower than the lower threshold voltage for the first time. Clearly, there is no chatter in the Schmitt trigger output. Let us now plot the input-output characteristics of a Schmitt trigger. For that, I will take input on the x-axis and output on the y-axis. Assume that applied reference voltage is 0, so upper and lower threshold voltages are equal and opposite. Let us say input starts from this value and increases. Let us also assume initially output is positive saturation voltage. As input increases, at some point it becomes greater than the lower threshold voltage. Does the output switch? No. Output right now is plus Vsat. So reference voltage is the upper threshold voltage. Output is plus Vsat, so the next time it switches is when the input becomes greater than the reference voltage, which is the upper threshold voltage. So unless input becomes greater than the upper threshold voltage, output will be plus Vsat. Now when input becomes greater than upper threshold voltage, that is when the switch happens. Output switches from plus Vsat to minus Vsat. Let us say input increases further. Does the output change? No, because now the output is negative Vsat. That means lower threshold voltage is the reference voltage. Output is negative Vsat, so next time output switches is when input becomes less than the reference voltage, which is the lower threshold voltage. So if input increases, output will be constantly at negative Vsat. Let us now try the opposite. Consider input is decreasing. It is somewhere over here now and it decreases. Will the output switch? No, output will still be at negative Vsat. Let us say input decreased and it went below upper threshold voltage. Does the output switch? No. Lower threshold voltage is the reference voltage now. So the next time output switches is when input reaches over here and becomes lesser than the lower threshold voltage. Till then, output will be constantly at negative Vsat. When input becomes lesser than the lower threshold voltage, output will switch from minus Vsat to plus Vsat. Let us say input decreases further. Does output switch? No. The next time output switches is when input becomes greater than upper threshold voltage. So if input goes over here, output will still be at plus Vsat. So this is the transfer characteristic of a Schmitt trigger. We have seen transfer characteristics of a normal. For a zero reference voltage, it looked like this. Every time input crosses the reference voltage, which is 0 volt in this case, output switches. Simple. The switching happens exactly at one point, right at the reference voltage. The curve is sharp with no gap. But in the case of a Schmitt trigger, it is not a single point. We have two switching levels, the upper threshold and the lower threshold. On the graph, this creates a loop instead of a single line. As input increases, output switches only when it crosses the upper threshold. As input decreases, output switches only when it crosses the lower threshold. If the applied reference voltage is non-zero, characteristics of a normal comparator would look like this. Instead of switching at 0, it would switch at a different point. For a Schmitt trigger, if applied reference voltage is non-zero, upper threshold voltage and lower threshold voltage won't be equal and opposite. The graph might look like this. This phenomenon is called hysteresis, and the difference between upper threshold voltage and the lower threshold voltage is the hysteresis width or the hysteresis voltage. We could say Schmitt trigger is a comparator with hysteresis. Hysteresis is what makes a Schmitt trigger stable. No chatter, no noise issue. Let us now solve a simple problem. We have to plot V out versus V input of the circuit given over here for reference voltage being 0 volt and for reference voltage being 5 volt. Let's take the first case when reference voltage is 0 volt. In this case, upper and lower threshold voltages will be equal and opposite. Upper threshold voltage will be plus saturation voltage divided by R1 plus R2 multiplied by R2. We have all the values. Even saturation voltage is given, it is 12 volt. We get the upper threshold voltage to be 1.2 volt. Since reference voltage is 0, we do not really have to find the lower threshold voltage. It is definitely going to be negative 1.2 volt. If we plot the graph, this is how it will look like. We will have hysteresis between 1.2 volt and minus 1.2 volt. Let's take the second case where reference voltage is 5 volt. Upper threshold voltage will be given by plus Vsat divided by R1 plus R2 multiplied by R2 plus reference voltage divided by R1 plus R2 multiplied by R1. We have all the values. That gives us the upper threshold voltage 5.7 volt. To get lower threshold voltage, all we have to do is put negative Vsat instead of plus Vsat. And that gives us 3.3 volt. The loop in the graph will be between 5.7 volt and 3.3 volt. It will look like this. So that's all about it for today. See you in the next video. And please don't forget to subscribe.